So today we're going to go into tensor fields. Tensor fields for me were like Fourier transform. First two times I heard about the Fourier transform, I was like, what in the heck are they talking about? And then the third time I was like, this is so obvious, I don't see why everybody doesn't get it, right? And so hopefully we'll be looking at it 2 or 3 times today and get you over that hurdle. And then talking about how to visualize things. So note, somebody tried homework 5, got started already, and realized you can't load the data the way it says you can in homework 1. So I'm going to visually tonight go figure out how to redo that and look for a new version of the homework tomorrow. Last year, homework 1 we used VTK header. This year we're using nerd format. Nerd format's nice because you can have a detached header, but apparently it's not nice and it didn't do something with this data set, so I'll look and see what's up with that. Mute.
Super absurd based
We need more jargon in this sentence.
Nematic liquid crystal is a state of matter between solid and liquid states, wherein thread-like molecules have local alignment but no global structure. This alignment can come in one of 4 types: uniaxial, where most of the molecules align along a single direction; biaxial, when there are 2 major axes of alignment; isotropic, where there is no average alignment; and negative uniaxial, when there is an overall director, but most of the molecules are aligned in a plane perpendicular to that director. The Q-tensor describes an NLC system. To visualize the Q-tensor, we utilize a set of 4 metrics. These metrics measure the amount of positive and negative uniaxiality, the amount of biaxiality, and the amount of isomorphism present in the alignment. These metrics form 2 baryocentric spaces, one for positive alignment and one for negative alignment.
What the hell is he on
Baryocentric
about?
just means that they're the corners of a triangle with values in between.
Baryocentric?
Barycentric.
Barycentric.
Yep. It just means that they form these two little spaces that sit next to each other.
So
Okay.
they deform based on,
The coordinates in that barycentric coordinate system.
okay.
In other words, this one merges to this one morphs to this one, and somewhere in between you get a mixture of the 3.
You
Okay.
can also
Depending
do
on kind of where you are along this three coordinates and where the corners of the triangle are.
Okay.
Within each space, the 3 relevant metrics are used to determine the shape of the glyph. These glyph shapes are physically motivated. A uniaxial glyph has rotational symmetry, whereas a biaxial glyph has 2 axes of reflective symmetry. The glyphs themselves are created using a subset of superellipsoids created from our metrics.
So superellipsoid is just a family of shapes in 3D, and this is a subset of that family of shapes. And so it's a way of parameterizing multiple parameters. You get their ellipses, but they can do other things besides ellipsoids, and so they're super ellipsoids. Ellipsoids are a subset of ellipses.
Wait, so there's a UU plus UI?
Thus, our glyphs are both perceptually and mathematically continuous. 3 types of glyphs have previously been used to visualize the Q-tensor: boxes, cylinders, and ellipsoids. Each can represent one particular type of alignment in an NLC system, but none can represent the entire range of possible alignments that exist in such systems. In addition, all these approaches introduce visual ambiguity and force the use of an offset which distorts the natural Q-tensor. Our NLC tensor glyphs provide a direct method to visualize the components of an NLC system. In addition, they can be generalized to any real symmetric traceless tensor without the use of offsetting or the creation of glyphs which are visually ambiguous.
All right, so the main point of the paper was to design a glyph that looked like the thing was trying to represent and was not ambiguous about what other things it might be representing.
Is it important to know what a real symmetric traceless tensor is?
Get into that.
Okay.
That'll come in the definition. These are just the previews. here, they're trying to look at how stress is distributed on a hip replacement, right? And so they're doing a simulation of if we put a point load stress on the new joint here, we see how that stress propagates down through the joint. And the idea is, our stress is being concentrated somewhere that's going to cause a new breakage, or have we done a good job in designing this implant so that when it goes in, it'll last a long time?
So
And is that other vector a,
So purple is compression,
okay.
sorry, green is
Tension,
compression,
yeah, purple's
and purple
compression.
is tension.
Tension.
Yep. And to throw in some jargon, these are going along the major eigenvectors that we'll talk about later in the lecture. It's basically saying this is the direction that stress would propagate through there. And then they've got a kind of a magic lens technique that you can look through the outside and see more details of what's going on the inside.
And tensors are modeled based on the structure of the bone and all that, or
So,
it must have something to do with material properties of the
yeah, they run,
thing.
they run basically simulations and understand what they're. So now this is saying, okay, that was the real bone, right, and how it responded. Now we've got an implant that is this piece of metal that's not actually flexible in the same way bone is. It's attached along this boundary. And so what's that gonna do as we go through that same force path that we would have gotten during walking, for example? And it shows that there can be some concentrations through the ends of this that are different than we saw with the natural bone, and give some idea of, how that's gonna, cause discomfort or cause, motion or cause breakage of the bone inside.
pretty dramatically different.
Yeah, I learned a lot of things in this class I didn't want to know about medical procedures.
That looks like it's really going to screw up your bone. Or your
It's certainly
leg.
putting a lot of tension and compression right there at the same.
Well, it's much more bifurcated. Like there's like purple and green, and like the other one they kind of twisted around
They kind of
together.
were separate.
It was more distributed. Yeah.
Yep. This reminds me that when I was growing up, the Bionic Man was a show you always liked to watch. This guy who had like a bionic right arm, and bionic legs, and a bionic eye. And they would always tie him together with handcuffs, and he'd always break the handcuffs, right, with his one bionic arm, right, which is like having the kind of solid thing in your bone, like it's indestructible, except the other arm isn't. So anyway, this is testing out how the Bionic Man's going to work well when he jumps off the roof.
What is this now?
Sorry, I missed it. So this is changed with respect to physiological state. So this must be the subtraction of those two fields and the kind of the remainder of the bone that's in both of those simulations to see where there's going to be concentration and where there's going to be reduction in force. So this is then computing the data set, which is where are the differences and how big are the differences, and showing that directly. All right, so tensor fields. So one way to think about tensor fields is a mapping of input vectors to output vectors. All right, so this is, you've got a three-dimensional space, you've got a vector field in that three-dimensional space. The tensor field takes that input vector field and spits out an output vector field. Right? So if you think about this with the stress strain, you apply stress at some location in space, and little tiny deformations of every voxel in space happen, which distribute this change in vector field throughout space. So strain and stress is a tensor field, right? How stress causes strain in a material. Another view, if your mathematical view, is kind of an n by n matrix for n space. So it's a 3 by 3 matrix for 3 space. Let me make that light stop flickering.
Now you multiply a vector by this matrix and it transforms it.
Into another vector.
So it's a function on vectors.
It is.
So what,
Sorry, it's like, there we go. It's off now, so it shouldn't keep
was
making
it
materials.
malfunctioning?
It was like
flickering
shorting out
for
or
a
something,
while.
right?
Might want to, that sounded like something that could start a fire.
Yeah, that's what I was worried
Might
about.
want to report
Right,
that to,
somebody could email to help. Yeah,
Yeah. I know.
help@cs.unc.edu, yeah.
Is that the email address?
It is.
Yeah.
All right, so yes, it takes an input vector. This is saying the same thing, right? It's a 3 by 3 matrix. You stick a 3 by 3 vector in, you get a 3 vector out, right? And that's kind of a mathematical view of the same thing.
What's the room number?
Citizen 007.
So it's the idea that at every point in space, there is one of these matrices, or this function has
There's a nine,
meaning,
yep.
and you stick so it takes as input a point in space and a vector and gives you a vector back.
Yep,
That's it?
that's it. So that was the third time. For you, that was the charm. All right, good. So we'll keep going. So a subset of this is the symmetric second order tensor fields, right? And so this is basically not quite the same as a symmetric trace suspension. So this is saying, okay, you can visualize this as an ellipsoid, right? So you take, kind of strain is this way. You smush this little voxel of space. Maybe it isotropically gets smaller or bigger. Maybe it flattens into a pancake. Maybe it, elongates into a cigar, right? And so you have kind of three axes along the ellipsoid. Each of the axes has a vector of growth or shrinkage along with it, right? And so these are the eigenvectors associated with this thing. So these are vectors. So an eigen means same in German. An eigenvector means a vector that's the same, right? So if you stick one of these vectors into your tensor field, it comes out pointing the same direction, but might get longer or shorter, right? So in a rotational field, right, there's one eigenvector. It stays the same. There's two others that don't. In this the symmetric second order tensor field, there's three eigenvectors. These are the directions that can be squished or elongated, but nothing rotates, right? And so you're basically, but they don't have to be axis aligned, right? So the eigenvectors don't have to be in the coordinate system of the room. They can be any arbitrary direction, but they kind of vectors in those directions stay the same, although they may get longer and shorter. Okay? And so one of the ways we're going to visualize these are with ellipsoids, right? And if you want a more general case, then you have to go to hyperellipsoids because you can't render ellipsoids.
So for a given matrix, you can generate some ellipsoid that allows you to visualize that matrix?
At a location in space, if it's a symmetric second order tensor field.
If it's a symmetric second order tensor field.
Right, so if it's symmetric in second order, then if it's symmetric, you can essentially treat it as, all right.
Okay.
So the eigenvectors are then the directions on which these vectors stay the same, and the values are kind of how much you scale each of these eigenvectors. So the major eigenvalue is the eigenvalue associated with the one that's at the largest stretch, and then there's the middle one that doesn't really have a name, and the minor eigenvector goes along with the smallest eigenvalue, right? So that's going to be important to go on. So then a rotation field is another subset, right? It's not symmetric second order. It's something that's got a rotation at kind of every point in space, and it's got one eigenvector, and that's all the eigenvectors that it has, because every other vector goes to a different vector. All right, so some questions that we can ask about tensor fields. Is it anisotropic? In a specific area. So what's that mean? So isotropic means the same in every direction, right? And so if one of these ellipsoids, if it's a sphere, it can get smaller or bigger, but doesn't change its shape. Anisotropic, there's two kinds in 3 space. There's stretching into a cigar shape, and then that's where there's one large eigenvalue and two negative eigenvalues. And then there's one where it turns to a pancake, where there's one negative eigenvalue and two positive large eigenvalues.
So
right?
what is that? Okay, what's the identity tensor field?
So it has 3 eigenvectors that could be any direction, and the eigenvalues is all 0, is all 1.
And what shape would that be represented by?
It'd be a sphere unit size.
Okay.
So any vector that goes in comes out the same.
So the cigar one, it's going to tend to go this way or this way, is that
It'll
it?
stretch the local space along the major eigenvalue, and it'll shrink it if it's also volume preserving. It will shrink it along the other 2.
So if I come in this
Eigenvalues.
way to this cylinder, I'm going to get shrunk down. If I come
Vector
in
pointing
this
that
way,
will shrink. Yep.
this dimension will get shrunk and the other one will get elongated.
Yep.
Okay. And then that funny top-shaped one.
Right. So that's not a.
Oh, so
symmetric.
it gets stretched like the surface of the thingy, of the.
Yeah.
Yeah. Okay.
And that's, spheres got
Sort of
turned inside
funny.
out in that
Yeah.
way, right? And so it's not any more symmetric second order tensor field.
Cigar-like.
Yep, and so, there's another question, is where would material move? Right, so this one shows up kind of both in vector fields and in tensor fields in these questions. Severe rotations. And then, stress causes strain. And then there's a question of, does it work in 3D? Right, and so we did 2D scalar fields and 3D scalar fields. For vector fields and tensor fields, we're just grouping them all together and kind of thinking about, does that work well for 3D? All right, so that was kind of the second time. So we've got a different set of classes of techniques, right? There's glyphs, which we're going to have more of this than we had previously. Stream indicators, hue and texture, deformed surfaces, and then computational, kind of finding the traces and showing them. This is what we were seeing as eigenvalues. Some particular techniques to show rotation fields, and then a separate discussion of haptic displays of tensor fields. All right, so flow probe we saw in a vector field visualization, right? You can show all the things there are about a vector field, but what happens to the vector field is in fact a tensor field, right? So the water is there in the river, it's flowing in one direction, it rotates as it goes in that direction, it maybe rotates in a different direction as it goes in that direction. The volume increases or decreases of its local element, so it's diverging or converging. And if its neighbors are moving faster than it on one side and slower on the other side, then there's shear, right? And so here we've got basically a 3x3 matrix with a local frame where x is kind of the forwards direction in this diagram. And so acceleration is the change in x as you move in x, right? So if as you go forward, you speed up, you have a positive acceleration, right? If you slow down, you have negative acceleration. Shear is the change in y and the change in z as you move in x, right? So this is kind of how things linearly change in that direction and this direction. Curvature is here, and then kind of convergence, divergence, and torsion or rotation are down in these off vectors, right? So this is kind of how things change. X changes, y changes into z, z changes into y as you move in x, right? And so this is kind of showing how you map these tensor quantities onto this glyph so you show all the parts of the tensor, right? So that's our kind of third tensor definition. Hope you got it. Here we go into the visualization techniques. All right, and so this is looking at this glyph applied to two things. On the right is a tornado, right? Kind of a funnel cloud going up. So tell me what's happening down here at the bottom of the funnel cloud.
What do colors mean?
So yellow was the acceleration.
Green, yellow 6, green is...
So it's shooting, it's going up faster. That means it's converging a lot, right? So the air is coming in and squishing there at the bottom. And then the length of the blue vector is kind of the speed, right? So it's moving slowly, it's coming together, it's compressing, but it's starting to accelerate, all right? Then we get up in the middle of the tornado, what's happening? It's no longer accelerating, it's spinning, it's twisting a lot, yet it is no longer converging or diverging, right? And at the top, it's kind of slowed down, it's still twisting some, and it's no, right, so it's, the vacuum's coming in, spinning up, going up. We can't tell at the bottom if it's spinning because kind of the cone has gotten in the way. We can look from a different viewpoint here. All right, so this is describing pretty well what happens inside a vortex going up.
Is the black ring just a border, or is
The
that...
black ring is just a reference frame,
Okay.
right, that tells you this is the shear and divergence and convergence and everything with respect to this. All right, so this is showing inside a piston as it's pulling out and sucking air and pushing it out there, what's going on at different locations in the field, and there's all kinds of interesting behaviors happening. These things are getting torqued around every which way.
So the tornado one you definitely could represent as a vector field, and it would make just as much sense as this picture, right?
If you're asked, so
We could have, arrows
You
of
could use-
the
you could
particles
use-
coming in and going out, and it would,
except for occlusion, yeah.
Yeah,
So if you're asking, could you come up with a visualization from which you could infer all the quantities of these? Yeah, that'd be another technique. Could you do it as compactly along the center line of the vortex? Probably not.
I guess it depends on what question you're asking, right?
Yeah.
But this
It
will
always
give you more information, right? Like for example,
This gives you more information about one point, unless you had lots of vectors, you could understand them all around.
But if you think of a tornado, like at the bottom you have less number of these, but
Mhm.
squished together, and
Mhm.
when it is like towards the top, it will be like less in density, but again you'll have all the information at all the points.
That's right. So the glyph, in this case, gives you much more information at a fewer set of points, and the arrows give you less information at a more set of points. And as you said,
Yeah.
depending on which question you wanted to ask was the one you wanted to.
It's also,
Okay.
yeah, and you could see this without it moving. Although it's not immediately obvious that that's a tornado if you were to just put that up on the board, right?
Well, it is now to me that I haven't analyzed it. But yeah, you have to analyze the glyphs to understand them. That's true.
Yeah.
All right?
Well,
So
are you going
this-
to talk about the other one?
And so this is a more complicated flow, showing kind of what's going on with all these things inside the cylinder. And there, it's complicated enough geometry that you're kind of glad to have a glyph showing you all the things that are happening right there, as opposed to a swirling set of particles and a sorting set of vectors. All right, so we saw this one before, and nobody asked for chocolate, but too bad. And so this is the overpowering chart jump, right? So this is, you look at this, and Tufte talks about this, is mostly what you see is this amazing grid, right, which is not the focus of the visualization. That should be kind of in the background, you know, a little more subtle, but nonetheless, it gives us kind of a flow along one of these lines and much more detail at points along this to see how the shear is moving and so forth. All right, so one way to show these symmetric second-order tensors is to map the eigenvectors, the major eigenvector to a bar, the two minor eigenvectors to a ring that goes around the bar, and that ring turns into ellipse as those eigenvalues are not the same. And there you go. This is a similar thing where instead of just a line around this, there's actually a red ring. It's kind of a red cylinder, or a thin cylinder around this. And so this is showing the response of stress, the strain response of stress inside this cube, right? So this is a point load pointing straight down. Green lines in this case show compression, and red shows tension, right? So what's happening here at the top is it's getting compressed this way and it's stretching out sideways. So there's a red ring around a green compression thing in the center.
It's very hard to see.
And yeah, I should make the picture bigger. All right, so these are these hedgehogs. Again, colors here, you know, red and green have been reversed, but there's an ellipsoid kind of cylinder, a thicker one around a thinner inner cylinder, a very similar technique. And you can see that these are all compressed in kind of coming out of that plane, and so the tensor field is being compressed.
Rainbow color
There's
map.
Rainbow color map.
Thanks, someone else over here had it.
Could be picky about the red, green, too, for color blocking.
Yeah, we're not going to be picky about the red, green, color line. Only because I'm not red, green, color line. That's not fair, right?
So,
All right, so this is looking at a mouse brain, spinal cord, to understand kind of how diffusion happens inside the spinal cord, all right? And so as the connecting parts of a brain go together, water can diffuse along those fibers, but not across those fibers. If you have kind of a breakdown in the fiber structure, then you get diffusion, free diffusion in space. Or if you have fibers crossing each other, you tend to get kind of a flat area where water can move this way and that way, but it can't move out of the plane. And so this is looking at different regions of, come on in. It's that one.
turn it back
I'm
on.
not gonna turn it back on.
The middle one or the back?
That one right there. How's that for help?
Turn it on so he can hear it.
Cracking.
Good, that's the answer.
It's clearly broken.
All right, and so this is a 2D slice. So this is showing you on the 2D slice the matrix, right? So this matrix is symmetric, which means this is the same as this. Right, so what we're looking at here is a 3x3 matrix where there's an image at every place in here, right? So this is the image of the XX term, the image of the YY term, and the image of the ZZ term, right? And this is the image of the XZ and the image of the Z X. So this is going to be the same, this is going to be the same, this is going to be the same because it's symmetric. And so really you can only look at the upper part. So this is the same image, but at every point there's an ellipsoid showing you these components, right? And so rather than trying to look at a pixel and trying to figure out which direction would this water flow, right, even harder than turning it into a vector field, this says, okay, along these regions here, water is flowing up and down the spinal cord, right, in and out of the plane. It's the slice through the mouse and Rossby-Carl slice. In the middle here, there's more pancakey things, right, and so it's more flowing in a plane in there. Here, it's more broken up, right? There's flows near each other changing, flows other places changing different directions. So this is a 2D slice through a 3D data set showing you this kind of 7 or 9, however you want to count it, dimensional tensor field at every location sampled in space, right? And I think this is just the magnitude image to give you an idea of what the kind of product of the eigenvalues is. All right, so anisotropic rate of diffusion here is in 3 dimensions. There's 3 orthogonal eigenvectors in 3D, and the major one goes along the kind of major axis of these things. In this case, it's got non-negative eigenvalues. And so you can think about if you put a drop of water right here in the middle of one of these ellipsoids, this is the way it would tend to move, right? Up and down, or out, or sideways as it goes. All right, so it gives you values of every point in space. Spheres are isotropic diffusion, and a larger ellipsoid means that there's a faster rate of diffusion. So you can tell rate of diffusion and direction of diffusion and kind of how anisotropic this diffusion is on these things. All right, and this is kind of a detailed view of that first image, just to give you an idea of what's visible.
See the problem that the ones that you're looking straight on, you can't see the magnitude.
Yep. All right, so this is a technique that's doing the same thing, but instead of the third dimension being a third dimension, the third dimension is the frequency of the color pattern along this ellipsoid, right? And so now you're trying to decide, okay, in 2D this is this, and the third dimension is angled according to how fast this color is changing. Not as easy to see as the previous one. This was done because what it does is form texture patterns on the image that highlight where there's regions of same thing, right? And so the physician here is like looking for, is there pathology? Well, I know what pathology looks like because it makes this interesting texture pattern, as opposed to, can I understand very clearly exactly what's happening at this point in space? And so this is kind of looking for a gestalt, where are the areas of differing values, and then you might switch to this technique to drill in and see what's going on at that value, or just put the numbers there if you want to query it to see what's going on. And here, the transparency of these fade in and fade out depending on, I think, the magnitude. And so where there's low diffusion, you just don't have anything shown there. All right, so on the left here is disease, on the right is healthy tissue. And I'm not completely convinced that I can immediately tell you which of those is which, but I can certainly believe that the people who wrote the paper could instantly look at these and tell you which of these is this. And so I guess these are a little bit larger than these. There's more saturation over here than over here. So there's some differences you can see in what's going on. All right, so we looked at this before. This is looking at the flow over a blunt fin, and the background is pressure. Then the ellipsoids show you the rate of strain tensor, and the vector field is shown on top. And again, the rate of strain tensor, the changing size of those let them know, since it is volume preserving flow, the fact that they're getting smaller meant that there was out-of-plane flow in that. And they weren't expecting out-of-plane flow because the simulation had basically a uniform geometry in that direction, but nonetheless little kind of eddies got set up when they did the simulation. All right. Other techniques for doing this, right? So this, you can take your ellipsoid, and when you look at it in space as an unlit, untextured object, it's kind of hard to tell the shape of what that is. If you turn that into 3 stripes, now you're getting a better understanding of those ribbons, what the shapes are. You can do 2 ribbons. You can do, we saw the kind of the ring with the arrow through it. This one has the benefit that it draws your attention to the major eigenvector. You look for the red arrows, and this gives you kind of a pattern to flow.
But it's going to be very hard to tell what the circle is doing because of the perspective distortion, right?
Nope, it turns out perspective distortion in the image works the same way it works in the real world, and your brain is used to that. If you do orthographic projection, it actually turns out to be a little more confusing. Astounding that we would be better.
You can be able to do relative Like, is this one squished as much as this one, kind of thing?
I don't think so, not at far
Yeah,
distances.
not so good, yeah.
Yeah, quantitative, but not so sure. So this is looking at uncertainty in a vector field, right? So this is saying, here's where the vector field starts, here's the average endpoint, but here's the range over which this goes, right? And so it's kind of more uncertain in this direction, and then this, and then least uncertain across that way. And then we saw, this below 4, and here, again, I should maybe put the sad face on this guy.
Mr. Potato
This is
Head.
the Chernoff done in 3D, so you can map arbitrary variables to his expression and get some idea of what's going on in this case.
Is the Chernoff
My
fixed?
guess is that that's the one that lost the user study, right? And it was in there so that it would lose the user study.
18 parameter, too.
Yeah. All right. So this was the video that we saw kind of at the beginning of the lecture, where you've got kind of a uniaxial alignment of these elements in space, and then you've got a biaxial alignment of these things in space. And so this is their glyph, compared to the others. And we looked at this, basically, they call it a barycentric coordinate system. So what that means is there's a coordinate here, and a coordinate here, and a coordinate here, and you kind of interpolate those 3 values across the triangle. And so it goes from each of these shapes to the other, so you can know any place in this space what the shape is, and it kind of gives you an idea of what the orientation of these crystals are in there. So this one is like what I was talking about with the diffusion fields, right? That you've got some going this way, and you've got some going that way, but you don't have any of them going the opposite direction, right? But it's not really like you can freely diffuse in there. It's more like you've got a couple directions you can go in there, but you can't really go in the 3rd direction. And so that distinguishes this case from just a pancake, where you could actually flow in any direction, right? So the pancake shape is more like flows 2 directions. This is more like there's 2 directions in there individually you can move. And then I zoom in on a section of that. Again, so these are now untextured glyphs. It'd be interesting to think about if you add texture, could that improve the shape of these, understanding of the local shapes of these. Of course, you're adding texture, you're adding detail, and so there'd be a little trade-off with that. All right, so Gordon Kindelman and Thomas Schultz looked at, okay, we want to look at symmetric 2nd-order tensor fields, and they came up with their own family of glyphs that included color to show you where there are negative values versus positive values, and so all positive, all negative, some positive, and they kind of picked different subsets of the space and mapped them, joined them together so that they had continuous variation of glyphs between one space and another. And so here color is basically a nominal scalar field showing you which of the positive or negative are you at, so you don't get confused about which way things are going. So this is applied to the curvature of the ear, and so looking at the Hessian of the Laplacian zero crossings, describing the surface geometry of an earlobe, right?
Huh.
So Gordon Kindelman's a guy who's like, I need to explain to somebody how my simplification algorithm works, so I'm going to come up with a new glyph visualization technique to give them an idea of what my metrics are on the surface so I can show them why I'm doing the simplification. So
What does it mean to have a tensor field on the surface of an ear? Is this just describing the normal vectors, or the?
So it's describing the change in the normal vector in 2 dimensions in the 2nd derivative sense. The Hessian is the 2nd derivative over space, right? And so you've got a curvature up, curvature down, a saddle, so it's up one way and down the other way. And so this is describing all of those kind of 9 values in one tensor. All right, so glyphs, what can we use them for? Are they good at anisotropic?
Yes.
Yes, we saw that just now in the last slide. Are they good at sheet-like or cigar-like? Yes, we saw you can do the 3 different ways of doing sheet-like versus cigar-like. Where would water go from here?
Not immediately obvious.
Not so much. Yeah, maybe if you integrated through the things, yeah. Where are the most severe rotations?
Sort of, kind of.
So if you had the kind of flow tensor and it happened to be at one of those locations, it could do that pretty well.
Well,
Yeah.
the hyperbolic looking one is a rotation, isn't it?
The only ones that was rotation so far was the kind of the flow probe.
They didn't have a glyph for that? The glyph that was like was shaped like this?
Yes?
Well, there was a specific one of those. The one stop. No, stop. The one at the very bottom.
Yep.
That's not indicating a.
That's not a spinning top. Right, that's things going in two different directions in that plane. Now, you could say, I want to make a glyph that makes a spinning top, but then you wouldn't know which way it was rotating. But you could imagine that with a glyph you could show the maximum orientation.
But the third question would be answered even with the flow probe, though. Where would the water go from?
Well, it would locally. So the flow probe locally would tell you which way, but it wouldn't give you a good way to integrate. If you happen to be going up the center of the vortex, you're in good shape. If you want to know somewhere else, yeah, not as good, as some other techniques we'll see. All right?
Strain effect with stress.
Right, the strain effect would stress have.
Not
So those point loads showed exactly what strain effect a point load happened across the thing.
But no, that's what strain effect is the stress having.
Yep.
If I'm asking the question, if I poke it here,
Yep.
if I'm looking at it and I poke it here, what's it going to do? I don't know that it answers that question.
You mean the integrated?
That picture showed what happened if you poke it in a specific spot, right?
Yeah.
But if I'm looking at the data and I want to say, well, what if I poked it over there? Is it going to do something different? I'd have to do a different simulation or something, right? It's not going to tell me.
Right, so this is saying here are some set of stresses on the outside
Right.
of the box. It's a very simple one. What impact does it have on strain? You're right, this doesn't answer what would any point on the box have. I'm not sure you could do that with a single visualization. But this directly does show us, okay, here, everywhere in space, what deformation happened from this stress. All right, so now we've gone from glyphs.
Does this technique work for 3D?
Does it work for 3D? With the standard caveats of occlusion versus confusion, yeah. All right, so now we're going to do hyper streamlines, right? So just like we had particle systems and then streamlines from particles, this is similar. It's basically picking one of the eigenvectors and doing a streamline along that eigenvector, right? And so this is saying, okay, what happens, basically this is showing the major eigenvector, and it's showing that at this point is going out this direction and that direction. The medium and the minor then follow kind of the other two eigenvectors and show you kind of how much deformation there is in those two directions. And here they use the rainbow color map, and I marked it for showing probably magnitude.
The color shows the magnitude.
That's right.
Of what?
Of the
The whole lot?
which is the determinant of the matrix, I guess, in this case.
Okay.
The product of the three eigenvectors, eigenvalues, which I think is also the determinant of the matrix in this case. Yeah. So this is showing you where stress kind of gets distributed as it gets pushed on this.
So the direction of the sheet is the major eigenvector.
Yep.
The sort of deformation along that axis are the other two, and then the
Color is the
is
magnitude.
the overall intensity. And what is that?
Yeah, see, now you've gone beyond my first two questions I know the answer to.
You don't know what the picture is of?
I don't know what the picture's of. Sorry.
Need another sad face for that.
All right, so this is a picture of 2-point loads on the same surface, and this is showing, again, the major, sorry, this is here is going along the minor hyperstreamline, right? So this is the largest, the most negative eigenvalue, which is the compression direction, right? So in this case, it's compression. This shows you how the compression gets fed kind of through the shape, and then the size of the tulip on the other direction shows you how much deformation is scaled there is in the other two directions, right? So this is showing you that it's expanding out, it's getting much kind of dilated here. As it goes down, it becomes basically not so much deformation, right? This gives you kind of an exponential fall off in the deformation of the
What are
surface
the
as
two
you go
little
down in.
guys doing this?
And these are particular points, the directions that it goes down from, right? So you could pick a streamline in any location the same way you could do a streamline in a flow field, and it gives you that same flow. All right, so this is a momentum flux density tensor flowing past a hemispherical cylinder.
What is a momentum flux density tensor?
Yep, I don't know. So momentum flux, so momentum is the inertia of the cluster of air that's moving. The flux of momentum is how much momentum per unit time is moving through a region of unit size. And the dense, so that's the flux density. So this is the flux density of the momentum. So this is kind of how much stuff is moving through
Air
a particular
mass
location.
is
Yeah,
what,
that's how the air is going.
it's a fancy way of saying air mass.
Yep. And so
Okay,
here we
great.
can see it's getting a little vortex behind the cylinder, right? So the streamlines are crossing over each other.
Presumably the color is velocity or momentum or something?
Yep, something. All right. This is basically advecting a point along the eigenvector, like very much like a hyperstreamline. In this case, they've actually drawn a texture shape here, right? So this line gets kind of a higher frequency rumple on it to show what's going on in the minor eigendirections. Bless you. All right. So this is adding both a geometry texture, which is this ribbing, and a color texture to give you an idea of the different microgeometries. All right, so this is mapping color on top of a tensor field, or texture and color on top of a tensor field display. All right, isotropic in a specific area.
Yeah.
Yeah, we kind of had that with these guys, yeah? Not necessarily all three of them, right? Pancake versus cigar-like, we're gonna have a hard time with, but isotropic, at least in the other two directions, these guys are gonna show pretty well. Where would water go from here? This is much better with this, right? This is basically streaming along, or where would stress go from here, or where would the strain be distributed? Yep. Severe rotations.
Depends.
This is kind of like with the vector field display. You know, if you're lucky and you kind of capture one with the things going around, you get it. It's not going to fill all space.
I mean, you could even do it so you've got the streamline. You could have like lines on the streamline that twist depending on the rotation at that point.
Yep, right. So
Mhm.
you could add a trick, which is what they do with the flow probe. Is in fact put a texture on that shows you that's what's going on. Yep. So with tricks, yep. And 3D, you know, there's more occlusion here than there was with the individual glyphs, but still, it can be sparse enough to see things pretty well. All right, so now we're going to do hue and texture for symmetric second-order tensor fields. And so here, basically, is a vector flow by texture. The hue is by magnitude largest compressive eigenvector, and these dots show the degenerate points in the flow.
Did I?
No. All right, we need to make this picture bigger to see what's going on.
What the hell is that?
So this is kind of the diffusion of the texture according to the tensor in the two directions of the plane. This is showing dots, but also the separating surfaces between regions of flow to give you an idea of the geometry behind the cylinder. All right. This is saying, okay, what we're going to do is map color to show you the anisotropy. This is going to be a little challenging. So basically, there's a noise texture that is the input. They blur this noise texture by the tensor field, right? And so it blurs more where there's kind of larger tensor field, and it stays very finely textured where there's lower ones. Basically, they're coloring here by relative values of the three eigenvalues, right? And so the largest eigenvalue, the second, and the third. So if the red is much bigger than the others, then it's linear isotropy. This is like a cigar-like. So wherever there's a red spot, it's more cigar-like. Wherever there's green, it's more planar, and wherever it's blue, it's isotropic.
So is this
so
nominal
here,
then?
It's a continuous nominal. Yeah, what does that mean? Right? So it's basically, it should never be red, green, and blue at the same spot, right? Very bright. It could get unsaturated if it's kind of, well, it's not isotropic. If it's completely isotropic, it's blue. If it's kind of a flat anisotropic, it's more green. So this is basically a nominal coloring of the tensor field. Where is it cigar-like? Where is it sheet-like? Where is it isotropic, and then you just put the color in space, and good luck merging it together in your visual field, right? So there's some inclusion problems, but this is you know, give it a try. Give it a try. Okay, so this is fiber stippling for probabilistic tracks, and so here the stippling, whether it's kind of solid or kind of long, the stippling is controlled based on fiber properties, and then you interleave them to show color. So remember how we saw the interleaving of the fibers in the Vicky Interante's work? This is interleaving of the glyphs, and so we see yellow ones, blue ones, and green ones that kind of interleave to show what's going on at different locations.
So the colors are nominal?
Different
Yeah.
fibers here.
So
are
they're
shown.
nominal.
They're naming different fibers, that's right. And where they overlap, they kind of, you know, mix a little bit.
And the tensor in this case is just the orientation? Because they're not moving around, right?
So this is looking at, the word is MR diffusion. And so this is basically looking for tractography. This is how the brain is wired, right? And so this is our areas where there's kind of a high linear cigar-like shape, where there's a very, you know, a good indication of fiber tracks. And you want to understand which ones go past each other and how they connect to each other. So the tensor field is the diffusion tensor in the brain. And then they've extracted the tracks and tried to show those tracks with the glyphs.
But it's also going to be the shape of the actual fiber, right?
It's also going to be the direction of the actual fiber.
I mean, yeah. Okay.
All right. So this is very much like lick. They call it hyperlick. It goes beyond this. And so basically, you're starting with this uniform 2D texture, or you can do a 3D texture, and you blur the texture along the eigenvectors, right? So where there's large and isotropic, it just gets blurred. Where it's large and anisotropic, it gets elongated, right? And so here's anisotropic flow, here's isotropic diffusion, and so we're seeing anisotropic diffusion in a ring around here, radially out here, and kind of more isotropic diffusion in here. And so the two directions are blurring at a local indication to give you the two ideas of the eigenvalues.
Is that rainbow?
I'm going to say no.
Trying to preserve chocolate.
Okay, so this is taking that into the third dimension, and basically also whenever it's isotropic, you change the opacity to make it very clear, right? And so it's basically, you can see through it, where it's isotropic, this is anisotropic, and giving you an idea of sheet-like areas versus tube-like areas.
I don't know how to interpret.
And this is all the noise texture in 3D, basically blurred to show what's going on. All right, so texture. Anisotropic in a specific area, certainly with the color, you just do it directly. Tensor like sheet like cigar like, again they drew it directly with the color. Where would water go from here?
Maybe.
You could integrate in these guys, similar to the way you do, not as easy as the streamlines that directly showed it, but more densely, so kind of halfway.
There.
In that previous slide, was that a rainbow color map?
You said it wasn't.
I said I was going to say no for you.
I was trying to be nice.
All right, 2 pieces of chocolate.
So is water going to flow? I don't think that previous one you can tell where the water's going to flow, right?
Not that one.
Not
but
so much.
This one.
That one
a
maybe.
little bit better. Yep. And the interesting thing about this one is, oh, where'd it go? The answer here is dunno, right? And you can tell it's dunno. Whereas if you had a streamline through there, it would go somewhere. It doesn't have the error bars. This gives you a better idea of the error bars. All right. And in 3D, if you do a very strong kind of hiding of most of the areas, and most of the areas are isotropic, then yes. Otherwise, you're going to have a lot of occlusion problems with these textures in 3D, and you're basically going to see the surface of an object. All right, so let's look at deformations of sheets.
We'll allow that one.
There it is.
I meant on the video, I was joking.
Yeah.
In this video, we
You
use
make that
simple
big?
surfaces in either physical or computational space to interrogate the tensor data volume. We begin with a stress tensor field from a single point load problem. The red arrow represents the point load, the yellow arrow represents the surface normal and selected vector field. We deform the surface first by the resultant vector field.
All right, this is where I said there's going to be a lot of splaining to do, right? Because this is a 2D slice through this field moving down. They're deforming this slice by a magnification of how much is deformed in the material, right? So if you're lucky, these four corners kind of tell you where the slice is happening. And then this is how a slice, a flat thing at that level, would be deformed in a straight down direction, magnified by some gain to show you what you're seeing, to make it clear what you're seeing.
Very shiny.
Now we deform by the normal component of the resultant vector field.
So I guess that was the total deformation. This is the deformation in that direction. And next we'll see the radial.
And finally, the perpendicular or shear component of the resultant vector field.
So this is a mesh that's
Invisible.
uniform.
We
It's
deform by the
deformed.
resultant and move the surface in the field. Now the normal component. Finally, the shear component.
All
The
right,
shear
awesome.
component sucks.
Compared to what?
You can't see it. At least
Well,
I can't.
The color choice was very not,
There's no contrast.
Yeah.
Yeah.
yep, they don't use the rainbow. So this is looking at what rate of strain around a delta wing. Where's it coming up? There it is.
We use interactive deformation to study the strain rate from a delta wing CFD dataset. A grid slice from the computational grid behind the delta wing is deformed by the normal component of the resultant. Deformations in the direction of the surface normal represent tensil's rate of strain, whereas deformations opposite the surface normal represent compressive rate of strain.
All right, same splaining to do. Yeah, show the original thing deformed.
The strain rate deviator from a capped cylinder CFD dataset is visualized. Using surface normals, the cylinder is deformed by the resultant.
So here, rather than taking a slice through and deforming it, they're saying, okay, what happens to the surface geometry or air near the surface as this flow is happening?
Next, a grid slice perpendicular to this cylinder is deformed by the normal component of the resultant. Finally, the resultant is mapped to grid slice surface normal.
Wow. So here they're doing directional illumination, but the illumination is with the rainbow color map instead of with brightness.
Surface normals, and directional lighting is applied.
So.
What is it?
Yeah, it took me 3 times watching this. So it's like, you know, how much the deformation direction lines up with this lighting direction where the amount of alignment is not product is shown by the rainbow. All right.
Okay.
So this is trying to do multiple of these slices in the same scene, and here they've got it tuned so that basically the opacity is such you can see the first one and not the ones behind. Here's one where they've got the transparency set so that you can't see the shape of any of them, but you get kind of an idea of what's going on in the overall volume to it. All right, so this is trying to solve the occlusion problems by putting a grid in there, right? So in motion and in stereo, this is actually going to separate not terribly reasonably. Still wouldn't use the rainbow, but this gives you this kind of understanding of how the whole mesh would deform. All right, so this is taking the surface of a rectangle and saying how is this thing deformed, and it just deforms it, and then colors according to the magnitude of the deformation, or the direction, if it's positive or negative. So this is doing the same thing with a 2D slice. So it's saying, okay, if we put this stress on this object, this gray object, it deforms into the shape that is this yellow object. So it's directly going to show you what's going to happen to this thing as you press on it. And
But
here, the color is just nominal, the deformed shape versus the original shape.
That's not really a tensor field though, right?
Yeah, okay, you got me.
I mean, it's just deforming an object,
It's
right?
it's the strain, and the stress strain is a tensor field, and so kind of it's showing you the tensor, kind of what strain impact stress has on the outside of the object. So it is showing you the result, an integrated result of a tensor.
Yeah, but it's not showing me like where it's gonna break or.
You have to
like,
use your
where-
mind to figure out how things connect to each other. But the good news is the shape is pretty regular, so doing that is not too hard. All right, this is really not a tensor field.
What?
This is showing multiple deformations of a shape as this flywheel is spinning. And it gives you kind of, they do 7 kind of transparent versions of this, and you get an idea of where it's more likely to be and where it's less likely to be by how many times you kind of can see through it in that location. So it gives you this kind of view of the wobble going up and down as the thing is spinning.
I see.
All right, this is a similar one with wireframe, kind of showing you the extreme range of these deformations to give you an idea of the space that would be carved out as this thing is doing this thing. This is, the surfaces are actually made up of individual spheres, so as they get far enough apart, you get this kind of grid that shows you kind of, that gives you an idea of the separation. Whereas if you just had the surface, you don't have a good idea. So this is a mixture between the kind of the grid lines that we saw separating and just the surfaces.
Rainbow color.
Oh, is that what you were smiling for?
Just bring chocolates for everyone. It even has a little rainbow.
53. It's got the map right there. It's good. I've got 5 more slides and I'll be done. All right. So deformation surfaces, what are they good for? Anisotropic in a specific area.
Yes.
Yes. Sheet, tensor-like, cigar-like. Not so much. It's like, what did it do to the surface? Can't tell locally what it is. Yeah. Where would water go from here? Not so much. Where would surface go from here? Much better. Where would water go from here?
It's actually lying to you about where water would go, right? Because it's changing the surface, but not, the surface isn't actually, I mean, you know what I mean?
Nope.
Well, like, is it flowing down the daisy or whatever you call that, tulip or whatever? I mean, is that the right interpretation?
So, if you ask kind of where would a point up here go, you have to interpolate between features you can see, but I think it's giving you a little bit of that.
No, where would water flow?
Yeah, so, I'm sorry.
Yeah.
Water was a general term for the thing that is flowing by the tensor field.
The gradient,
This would,
yeah.
This would be, where's the gradient?
Hmm.
Integrated gradient. What strain effect would stress have? Yes, it's telling us exactly that for several of these things. So,
Rotation, not so much.
severe rotation, not so much. All right, so for 3D, if all you cared about was the boundary of the object, maybe. If you want to see the inside, we're going to have to slice it back into 2D to see what's going on. All right, so this is computed stream tubes and stream surfaces, and so this is, again, looking at inside the brain where there are kind of pancake regions of diffusion, where there are linear regions of diffusion, and when there's not. So the tubes basically flow mostly along a line, and it follows the principal direction of diffusion, which is the largest the eigenvector associated with the largest eigenvalue, the major eigenvalue. Cross-section is an ellipse, and saturation shows anisotropy. So more kind of colored red is more anisotropic, right? And so it's more, very clearly linear. Surfaces is where diffusion is larger in 2 dimensions. It's perpendicular to the slowest direction, so things would travel in the sheet. And again, saturation shows anisotropy. So strongly green means that it's really confined to the sheet here. Kind of an almost white thing, it means it can go many directions, but a little bit tends to refer there. Similarly for the red. So it's basically showing you those 2 different regions. And then they got some annotated landmarks to give you to help you as a medical physician to understand how these things are connected. All right, so this is a side view of that same thing, and so we can see some large sheet areas, some kind of tubular areas, and again they're using thresholds here to not display the data in most of the place, right? So unless it's strongly anisotropic, you don't see anything there, so we can see through to the parts that we care about. Right, and so this is the same thing displayed in a cave, right? So here they've got some stereo glasses and they've got 5 or 6 walls around, and they're tracking where this person's head is, and so everywhere in the room you're walking around in this brain and trying to trace which you're doing. This would be fun to do in your own brain, right? I'm tracing what I'm thinking about how I'm tracing. I'm thinking you can do it on the optic nerve and we can bring the whole thing together.
You end up with like a closed loop feedback.
I think about that. We'll talk about it after class. So this is basically running an algorithm to say, okay, where is it most likely to be the case that there's fibers, which things are connected to which, and then just draw me the fibers that are the things that we're computing. And then this is drawn on top of a couple of textures that show probably the amount of anisotropy in those planes to give you an idea that this bundle actually extends out through this area, not just along those central regions. This is another viewpoint. Again, this is tracing along major eigenvector. There's a plane that you're seeing here. This is the, I think it's called the corpus callosum, the thing that connects the 2 halves of your brain. And then there's the different connections that are going on one side and different connections on the other side. Here we've mixed colors. So what they almost always do is red means this direction, green means this direction, and blue means this direction. And you vector add these colors to get which way this fiber is tracing. So it's almost universal in this field. And so maybe the next paper will be, that color map considered.
Evil.
So this is showing you regions of high anisotropy that's flat, and then showing you the tubes of anisotropy that's tube-like. All right. Here we're doing this again for a 2D grayscale slice, and then pulling that from the middle. Here, there's a little bit, not as much contrast between the tubes, and so they mix together into one kind of a blur. Halos would help kind of pull one from the other. Doing cylinders that are illuminated would do that similar thing, because around the edges they would tend to fall off in brightness, and you get occlusion between those two. So this is the halos, right? And so this is basically no halos, and then adding halos and halos shifted back. So now you can't tell what's in front of behind here, and this helps you with that. The illumination gives you some idea of direction. That's preserved even with the halos locally. All right. So this is a whole environment for doing fiber brain connectivity tracing. So you're going to put a green probe in there, and it's going to highlight all the fibers that go from the green square anywhere in the brain. They're going to do the same thing with the red probe. Now you can kind of see from both those places. And now they're going to put the blue probe in there, right? And so now we've got a lot of mixed up stuff. It's hard to tell which thing came from which. So what they're going to do is they're going to ask a question like, okay, which fibers start in the green box, go through the blue box, and end up in the red box, all right? And so this query right now is the sum query, show me the union of all the things going through these boxes. But now they're going to switch to show me the ones that go along this path, right? And you can do these in 3D. And now they've basically stripped away most of the fiber tracks and are using this as a 3D selection tool with not only a beginning and end point, but where they went through. So if I did surgery and I cut this part of the brain out because there's a tumor nearby, how is this going to affect the connectivity between these regions? Are there other places that are connected that are similar there? What's going on as I go through it?
It's very bright.
It's very bright. So they're not using illuminated lines.
Yeah.
They're just making them all white. And there's no halos, so you can't tell front to back as well. Here, they're sparser, and you can start to get a better understanding of the shape, and then you can, of course, slice through and see what's going on in that slice.
So this is not about as much about direction as it is about connectivity, yeah?
That's right. Yeah, so it's kind of a tensor field connectivity.
So it's like an
Detector
integrated
system.
tensor field kind of thing.
It's an environment intended to solve a problem using tensor field visualization as part of that. That's right. All right. Again, this is looking at reduction from a higher field to a lower field by saying we're going to compute the fiber tract density. We're going to produce so we're going to first extract fiber tracts, right? Then we're going to splat these into space and figure out what the density of these fiber tracts is. And then we're going to turn that into a scalar field, and we're going to isosurface the scalar field to show you where in space there are kind of line areas, right? And so this is to answer a very specific question, kind of how many fibers per unit area are going through this location, how bad would it be if we cut that, or how important is this to the communication across the brain. And so then they've done surface shading versus fiber tract density, just doing volume rendering to give kind of two different views of this. All right, so tubes and surfaces. Anisotropic in a specific area. Yes, we get tubes or surfaces, shows the kind of cigar-like or sheet-like. Yes, it shows the sheets and the tubes. Where would water go? Yes, we're tracing along the fibers exactly where water would go. We're in a sheet, we know kind of the directions that it would go. Most severe rotations, yeah, doesn't really apply to this so far. What strain effect would stress have? Yeah, doesn't really apply here. So tensor fields, you can see things break down by the kind of tensor field that you're looking at. There's a bunch of techniques good for one, techniques good for another, and so forth. Does that work for 3D? You need to really ramp up on the kind of occlusion by removing things you didn't care about, and that helps a lot with these techniques. All right, another direction. So rotation field.
Rainbow.
And so this is not rainbow.
It's not?
Nope. It's actually little triangular prisms that are red on one side, green on the other side, and blue on the other side. And they were actually spinning with the rate at which the field was deforming space. And so you could actually see them beating against each other. Things that were the same spin rate would show with the same phase, and things that were different would show with different phases. And so the video, this is pretty cool. So this is looking at the question of, if you have a magnetic tracking system, and your floor is made of metal, which it is upstairs, how much deformation do you get as you walk around in your head-mounted display in terms of distortions of rotations in the field, right? So as you walk around, it turns out you're kind of in a bowl, and so everything kind of goes this way and this way as you walk around. And this was a way that they measured this, and they took the whole system outside where there was no metal, and they built a whole thing out of like plastic screws and wood, so that they had no metal, and they measured the system again to get kind of the best case scenario, and they wanted a way of displaying what this looks like in 3D. So this is a video that rotated and these things spun. So this is showing you kind of what the rate of deformation was around the display. And the fact that the colors strobed at different rates gave you a way to see subtle differences that you wouldn't get if you just mapped it to color in the display.
So the spinning was the magnitude and the orientation was the field line?
Was which way it spun, and the spinning speed was proportional to the magnitude of the rotation around that axis. Right, so a rotation field, each place is basically one axis around which it rotates, and then the amount of rotation around that axis. And that axis can be any particular direction. All right, so this was taking little gnomons, right, these little 3D axes, and they started out in a grid and regular, and then they would rotate to show how much deformation. Now here, perspective and viewing gives you a trouble understanding what's going on, so what they did was actually animate them from original to final, original to final, original to final. And so you could get an idea of how much they were moving over space by watching that over time. And here they use red, green, and blue for their X, Y, Z, and that's what we all did back then. All right, so this is integrating along those axes and basically taking a grid that there were no deformation, would be a regular grid, and it kind of shows you how much integrated error there is over time. And again, they animate it from the flat case to the moving case to the flat case to the moving case. So these are not hyper streamlines; they're actually integrated error along these axes. All right.
Asymmetric tensor fields have important applications in fluid dynamics and earthquake engineering. Previous analysis decomposes an asymmetric tensor field into different isolated regions with different deformation modes, including expanding, contracting, rotation, and stretching. Previous visualization for asymmetric tensor fields places hyperstream lines through the whole domain by following the eigenvectors in real domains, where the deformation is stretching dominant, and the pseudo eigenvectors in complex domains, where the deformation is rotation dominant.
Such a visualization makes the identification of different deformation modes difficult. In this work, we present a hybrid visualization to address this issue. Specifically, hyperstreamlines are used in real domains, and glyphs are placed in complex domains. Furthermore, an image space implementation is introduced, which enables the analysis of asymmetric tensor fields defined on curved surfaces with complicated geometry. In what follows, we demonstrate the use of our tool in the visualization of the simulated Earth.
What are the little dots?
So here, the Earth is moving along this axis. The color tells you which way is which. Here, it's spinning in little circles, right? And the color tells you if it's spinning clockwise or counterclockwise. And so the glyphs are trying to give you an idea of what the local Earth motion is in an earthquake, so you can understand the mapping of how things are moving.
So is this a slice?
This is a slice.
Spinning?
Particular Z. Yep. All right, so again, the model is there's spinning things moving this way, there's compressing things, there's expanding things, there's sliding things, and these are all the behaviors you can have. So they try to come up with a glyph that gave you an idea of each of these when you looked at it, rather than just had crossing lines that was ambiguous exactly what was happening in there.
Is the spinning like a nodal point?
It's like the Earth is, that
Twisting.
part's moving this way and this part's moving this way, and so
So it's in shear,
it's-
okay.
Yeah, very much like shear.
Except, no.
Except in one direction, yeah, it's like rotation. Yep, all right. So this is looking at tumor growth over time and how that tumor changes this area in the center of the brain where the fluid is. And so this is basically showing the deformation of one caused by the other. So one question is this tumor basically growing and eating through tissue, or is it growing and pushing aside the other tissue, right? And so this kind of lets you see, okay, here was the other thing, here's how it started. And so in this case, no, the tumor's pretty much growing and covering all the material inside. It's not pushing the other things out of the way.
Is this simulated or is it real data?
That is a good question, and I think it is real. It's really bad news for some people.
Yeah, that's
All
not
right.
good.
This is, right, this is a different case. So here, this is getting pushed out of the way much more, right? And so we're seeing the deformation of the 2D surface, but also the deformation of the 3D as it moves.
Am I seeing arrows? I
I
am
think we're seeing arrows, yep, which is maybe the velocity, the speed of motion of the surface scale as the growth of the tumor.
Problem with this is by the time you've got this animation, the patient is dead, so. Or gonna
Yeah.
wish they were, yeah.
Well, I mean, if you basically what you got the patient at the end, and the answer is, well, why did you wait so long to do that? That's a good question.
Actually, not always.
No?
Like, if you look through like a data set of like brain tumors, for example, like sometimes the ones that are really big aren't infiltrative, so they're easier to remove.
You just lose all that,
You just, yeah.
whatever's there, yeah.
It feels a lot better after.
All right. And so this is dealing with the problem of occlusion in 3D. What you can do is use haptics. So haptics makes a little robot arm, and you use it in reverse so you can feel around inside your data. We'll see some of this during the lab tour. And what they did here was they say, well, you can only tell about one point, but you can tell basically I'm constrained to move inside a tube if I'm in one of these tube-like areas. I'm constrained to move inside a plane if I'm in the plane area, and I'm not constrained if I'm in a free diffusing area. If the diffusion is very low, then I'm stuck, right? So you're basically feeling, by moving around, you can probe the local tensor field, and it tends to guide your hand. Okay, this is connected to this, but it could be connected to that, it could be connected to this, whereas these, no, pretty much that's the only connection between them. And then the kind of slice would follow as you moved around and show you traces behind and give you a color of the anisotropy as you went. And then in the plane, they've got kind of these ellipsoid glyphs that show you the two-directional display. All right, so this one, I took my giant table of ugliness and compressed it down into a lookup table, right? And so if you're trying to do, is it isotropic? These are the things that kind of tend to work. Is it cedar cigar-like? These are the things that tend to work. And again, this is me in the classes from several years, best idea of what this is. This is not the same as, we did user studies and here was the answers and how they work. So this is how we think that they should work. Here's what I'm going to try first. but we aren't as a field to the point where we can know for sure that this is the ones that work. And then we got the whole horrible matrix, you know, down behind to kind of drill down, and then references to the work that we have elsewhere, if you want to look up some more things, and then the credits for the things that were in this display.